Okay, so, all right, so I'd like to show you what some sample traces look like. This is for the two-planet system HD 208487. And so here's the plot of the log prior versus likelihood as a function of iteration. And so I've thinned the iterations so by a factor of 10. So in total, I did 500,000 iterations. And we keep just 50,000. So here you can see we started far from the optimum location, just a random location basically, and rather quickly it gets into an equilibrium distribution. This is this S parameter that I talked about, the extra noise parameter. You can see it drops down here, and we end up with a distribution which is crowded around zero, but has a tail, obviously. Now, for the period parameters, here's P1 and P2, and you can see they're swapping. And this has to do with the fact that they're both free to roam through the entire frequency space. Here are the eccentricity parameters, and this is the K parameter. And then after the fact, we relabel, and when we relabel, this is what they look like. So now there's a single frequency representing the lowest frequency and a single frequency representing the upper frequency, and not much else happening. Really, there's, on the basis of these results, is just two periods. However, some slides ago, I mentioned that these other observers found that there were two possibilities for the second period, and I'm only finding one of them. That's a bit disturbing. So what's going on? Let me just show you what I call my periodicum plots look like. So here's, this is period versus iteration. And so the red dot here and the blue dot here at values just below iteration 0 represent my starting periods. And so you can see they jump up almost immediately to these two periods of 130 and 900 days, or roughly 900 days. You can see this is the log to the base 10 of the prior times likelihood versus period. And here I've normalized to the most probable, the maximum value of the log to the base 10. So you can see this goes up to 0 and 0 at this point here. And then here's the eccentricity versus period. So this one here has eccentricity going from 0 up to about, well, depends on the threshold I cut off here, but it's more informative. When I plot the marginal for the eccentricity, you'll see a distribution more accurately. This just shows the distribution of points, basically. And here's the K parameter plotted versus eccentricity. And so this mess over here, this rather broad mess over here, resolves down to sort of like a banana-shaped structure, where the bulk of the points here are actually down around low eccentricity values, but there is this tail that goes out here and corresponds to the higher eccentricity points at the higher period. So that's now that's using priors which are individually look like 1 over f for the frequencies, right? So I decided to play around and and change my prior to 1 over the square root of f to see if I could give greater weight to the lower frequencies, to see if it was possible to detect these planets. But before I show you that, this is just what the marginal distributions look like. And from our discussion yesterday, I clearly need to learn more about kernel densities and smooth these distributions. But you can see the eccentricity value for the higher signal-to-noise planet is still quite broad, and it looks like it definitely prefers something that's non-zero, although the distribution definitely goes down to zero. For the second one, you can see it has a very broad distribution going way up here to 0.7, 0.8 even, but the bulk is down at low values, so it favors a low eccentricity orbit. Here's the S value. You can see how it peaks up around S equals 0. There's really no significant evidence for any excess noise beyond the model of the two planets and the measurement uncertainties. This is what the periods look like, and you can see that this distribution doesn't look particularly Gaussian. That's probably as a result of that correlation, that banana-shaped correlation that is present. Okay, so if you change the prior to 1 over the square root of frequency, now I do detect a 28-day period coming in here. So now starting from the same two periods, I jump up and I still get dominantly the 900 and the 130-day, but this 28-day period, you can see the tempering is dipping down to that at regular intervals. And here's the eccentricity distribution versus period. There's still many more points at this, but it makes you wonder, well, okay, the prior is obviously affecting things, but more recently I've gone over to using both a 1 over square root f and a 1 over f for the exploration to see what evidence there are for other planets around. And I really should, when I loosely refer to these as planets, you should think of these as signals that could end up being good candidate planets, which with suitable n-body integration, we will be happier to say that they're real planets. So that's kind of the progression of things, but I tend to get sloppy and call these, well, it's a two-planet model as far as I'm concerned. Okay, so when I talk about a periodogram plot, it's really like a series of about 4 figures here that try and capture the different aspects of what we can learn about it. One of the things that you can do without doing an n-body simulation comes from work in the 1970s, 80s that showed that the motions of a system of a star with 2 planets that are not in a near low-order resonance would be bounded in some situations, and the 2 dominant definitions of stability emerged. One is called Hill stability, and what that means is that the ordering of the 2 planets in terms of the distance from the central star is conserved. So they will one will always be outside of the other, but that doesn't guarantee that they will remain bound to the system forever. They can still progress outwardly. And a tighter stability criteria is called Lagrange stability, which includes Hill stability plus the planets remain bound to the star, and the semi-major axis and eccentricity remain bounded. And so there's some nice results in a paper by Rory Barnes and Greenberg that basically you can take the output from your MCMC, samples from your MC solution, and run it through this Lagrange filter and find out, well, are they stable on the place? Are they Lagrange stable? And so it turns out that when I did that, both of the 2 period planet solutions are stable in this analysis. Well, this brings us to aliases. We're going to try and sort out, is one the alias of the other? Well, yes, they are aliases of each other, but which is the real signal? So let me just remind you a bit about aliases. This is all textbook stuff, but if you have uniform sampling, then you know that if you move into the Fourier transform space, then in the Fourier transform space, what you do is you take the transform of the, well, you have a bed of nails basically in a frequency transform for your sampling with separation 1 over t, and then that gets convolved with the signal, and the signal in this case is a sinusoid of 1.23 hertz, and in frequency space that's represented by 2 delta functions, one on the positive axis at 1.23 and one on the negative axis. And then I've also shown the Nyquist sampling frequency cut off here at positive frequency, and here's the negative frequency. So now if you convolve this with this is the spectrum that you would expect to observe, at least, you know, you expect to observe the positive frequencies. And so here you get, let's see, one at 0.23, one at 0.77, and one at 1.23, and then 1.77. And only one of these falls below the Nyquist frequency. And so this is the only one that you would be inclined to think was real, but in fact the true signal is up here. So it's not even it's not a real signal. So that's what happens with uniform sampling. And another interesting way of looking at this is to take 4 uniformly sampled points from a real signal, and then if you go back to that other diagram, you take the real signal and the artifact signals, and you pass them through these points. You'll see they all pass through the 4 uniform points. But if you move one of those uniform points to be non-uniformly, just move to non-uniform sampling just by 1 point, you now find that, of course, only one, the real signal, will go through that. All the other aliases don't go through it. And so with this understanding, I thought, well, Extrasolar Planets is going to be great because we won't have to worry about aliases because they're, you know, we have non-uniform sampling for sure. But it turns out the situation is a little more complicated than that. And there's this classic paper by Rebecca Dawson and how do you pronounce that? Yeah. Anyway, what they showed that because when you observe from the ground, you introduce inherent periodicity by the fact that you have to observe between sunrise and sunset. So all this phase space, you know, after sunset, you can't sample. So when we say we're sampling randomly, it means you should be able to sample randomly in phase. So there's a whole section of phase space we can't sample there. And then between star rise and star set, we were able to observe, but not otherwise. And so that introduces inherent periodicity, which shows up in the window function. So they were interested in wondering whether or not they could use the window function information. So if you take the transform of the observation times, not the amplitudes, just the observation times, you get what's called the window function. And so this is the case for GJ 876, where there were 2 possible periods that they were considering. And so you can see here are different ranges of frequency. So frequency is 1 over day. And here is a real, no, that's, okay, so this is an alias around 0 day. The green one is a yearly alias. This one here is, these are daily features. So there's one here and one here. So there's a sidereal day and a solar day. And here are multiples. This is a 2-day pair, and then there's a 3-day one here as well. So that was the window function that they were dealing with, and so they took their data, and here's their data here, and transformed in frequency space, and so you can see these peaks. And this was done using the generalized Lomscargo periodogram. So they display the amplitude of that, and then they have phase for each peak. They calculate the phase as well, and they use this phase dial. So here's the real data. Now here's simulated data, but simulated without any noise. So there were two candidate periods that they were interested in. One of them was 1.94 days, and the other was 2.05 days. So this graph here, or this spectrum here, is for the second row is the 1.94. And so we know in that case, since this is simulated, we know this is the real signal here. And all these other things are aliases. And then in the third row, the real signal is located here, and all the rest are aliases. And so what they've done is they've taken the envelope of the real data, and that's this dark area here, and they've overplotted that over the transform of the simulated data. And if you look carefully at the comparison for the two cases of a 1.94 day and a 0.205 day, you'll see that, especially over here, the simulation here doesn't show anything much going on, whereas there clearly is an alias in the real data. And here, this discrepancy here is not present here. This is a better match here. This is better as well. And this is better here. So they end up concluding on this basis that this is the real signal and this is actually an alias. So I thought, well, okay, great. We have a method. We understand how to determine the aliases. We have a scheme that seems to work. So let's try it out on HD 208487. And so here's the window function. So the window function is basically just the transform of the times. Now I decided to not use this window function exactly, but to, since the errors are quite different at different points, I decided to create a weighted unit window function. So I'll show you that in a moment. It turns out to not look very different, significantly different. So here we see there's a peak corresponding to the 1 year peak. Then there's this synodic month peak, which is the other dominant peak. And there is a big peak at 1 day as well, which is not shown on here. But, oh yes, here we are, 1 day. So there's a sidereal day peak and a solar day peak. So those are the dominant peaks. All right, so okay, this is the same thing, only it's a weighted window function. So just transforming the points using a weight, and you get essentially the same thing. And here's my attempt to repeat their analysis, and I've got several plots to explain here, and I stared at this a long time, and I started to go one way, and then I started to go the other way, and I ended up concluding there's no clear conclusion that I can get from studying the alias plots that they were using. So at this stage, the only basis for favoring one or the other is model comparison. And when you do that, I get a factor of 10 preference for the 900-day, but that is nowhere near sufficient to claim that it's definitely the only real signal there. So we're in a state of limbo on this one. It could be 900. It's more likely 900, but it's still a good bet that it might be 28. All right, so at this point, I thought I would go into the computer and show you what the FMC software looks like and make a few comments about it. You know, it's not super quick. And you have, in the example, I have 12 parameters. And to do a proper job, I typically would spend about an hour and a half running this on a 2-planet problem. I can get it down, I'm almost down to half an hour per planet. It sort of scales with the number of planets. So if I'm doing 8 hours, if I'm doing a 8-planet model, it can be done in about 4.5 hours. So it's not, it doesn't take a, it's an acceptable length of time, and that you can run an overnight job and, come back and look at the results and say, well, it's an 8-planet is doing a good job or not doing a good job. I'm going to go back to this to get out of this. And I just thought I would go to the book website to show you, if you're interested, how to get it. So if you go to the resources page here, you click on the resources, you'll open up this window here, and there are a number of resources. So here's the latest fusion markup chain Monte Carlo code for Mathematica 8. Unfortunately, Mathematica 9 and Mathematica 10 have included many new features, and they've slowed down. So Mathematica 9 takes 50% longer to do these calculations. Mathematica 10 isn't that much slower than 9, but it's become a memory hog. So I'm a little disappointed in that. So I don't have 9 and 10 because I'm not recommending them here, but they could easily be produced. Okay, so, and then there's some other resources here. If you're not a Mathematica user and you want to bring up the code and try it out, there is a free interactive player that you can download. And then there's lots of other resources to do with the textbook itself. Okay, let me try and bring up the code. Oh, okay, that's my mistake. I have to open it here. All right, so this is what it looks like. And if you're not familiar with Mathematica notebooks, they're not only your programs in there, but all your documentation fits in there as well. And I just have this brief thing at the beginning here, which shows the eccentricity prior that you've seen already. But it gives some background information on that. So let's just sort of walk through the layout of it. So there's a setup that just whenever you run a Mathematica program, you want to include certain things like multivariate statistics and error bar plots and all that's set up, and you don't want to have spelling check warnings all the time. So you typically have these sorts of ingredients, and you just execute that. And to execute something like this, you just go Shift-Enter. Right? And then the code that I've written is all parallelized, so it will use whatever CPUs you have, right, on your laptop or your mainframe. And so this laptop doesn't have 4; it only has 2. But typically, I'm running with 4. I did have an 8 processor one, but it's now aged so that an Intel i7 machine is faster than it. So you just launch your kernels here. In this case, I've only got 2 kernels. Here's the data. Let's plot the data up. So just a list of data that I'm extracting. And then I plot the data values here. And I've used as a reference time sort of the the mean value of the data. And so everything's referenced to this Julian day number, which is the date that is used for these observations. So here's the initialization procedure. So you can see there's 15 steps here, some of which the user, if you're wanting to look at a particular planet, you have to specify the number of parameters and etc. But there are others that you don't need to change and probably shouldn't change. But the beginning one, the initializing, so we have to decide, well, how many iterations are we going to do, and how many calculations do I want to do in parallel before. So there's a number of iterations in one parallel step. So I typically do 10. And then I can thin the observation so that I can store a certain fraction. And that's some number times n parallel. And so in this case, I'm going to thin it by 10. And the total number of iterations that I'll do will be 50,000 times 10 then in this case. So you can easily change that. The number of planets is 2. The mass of the star is 1.05. And of course, you need the mass of the star when you later on calculate the masses of the planets from the Kepler fits. And we're running 8 parallel chains. In some problems where you don't have the multimodal complexity, you only need to run one chain. It'll work just fine. But in this problem, you need 8 chains at least. Now, the number of parameters, I've just set that to 12 because there's 5 basic parameters for each planet, plus you have the velocity, drift velocity, and then we have this extra noise parameter, S. And in some cases, you want to include a slope parameter as well. So you'll have, if you like, an offset, slope, and then you'll have your Kepler models. I don't have a slope in this one. So this quantity NCS, I can, if I like, use fixed. I don't need to make. I can use fixed proposal distributions for some parameters if I want, and not tune them at all. And so by having this parameter NCS, I can say I only want to tune the first 5 of these parameters in the burn-in period, and I'm going to use some previous ones for the others. The total number of interesting values that I want to restore is NL, and that's NP plus 6. So there are 6 additional items containing things like the log prior plus beta log likelihood. And the N2L, which is NP plus 5, is just a special one which contains the log likelihood. Now, the next item here is the fraction of iterations employing correlated proposal sampler. As I mentioned, I have the independent, the I proposals and the C proposals. If the problem is very simple and I'm not worried about correlations in the parameters, then I can just turn that off or set this value to be something very small. But typically I will run that at 0.5. If I want the gene crossover operations to happen, then I set SWG equal to 1. I almost always do that. And this last option here is, so when we're tuning the period proposal distribution, I tune it on the assumption that the period will jump by a factor of 2. So I can. Brendan was when he was proposing, he chose a proposal. He didn't fix a particular proposal. He chose within a range of values, and so I allow this as well with this parameter here. So you can have 2 different range. So that one range is a factor of 2 larger than the other, or you can set that, and that gives you additional better ability to detect multiple peaks. So really that's all that's involved in the initialization. Then in starting parameters, basically you just fill in these tables here. You have to give you, on your plots you want to have, you know, parameters named, so these are the names of the parameters. You also want on the plots the dimensions to appear, so this is the array of dimensions. Here are my starting parameters, where the parameters are as listed here: period 1, eccentricity, 2 pi chi 1 plus omega, etc. And then for the last one here, the standard deviation, for the S parameter, I just set it equal to the standard deviation of the data. And then, as far as the proposal distributions are concerned, there is a module that, given the information you provide about the parameter and prior ranges, which come next, it will say, oh, that's a parameter of this type. It's an angular parameter. We know that that's modulo 2 pi or it's modulo 4 pi, and so we want to wrap around if we're proposing beyond that. And so there, and the period parameter I designate as type -1 because usually when we talk about these things, we're talking about periods, but as I explained earlier, we actually want to search in frequency. And so you always have to do a 1 over the frequency when you're making a proposal, because you're making proposals in frequency space. So that's the only reason I have a special type for that one. And so there are parameter types here, some of which have nothing to do with the Kepler problem. So basically, here's my template of parameter types that I used. And if you give the right parameter type, then the proposal distribution will do the right thing. So the prior search range, you have to specify that as well. So here's AV min, AV max for the different parameters. And in principle, you could use, and I do, sometimes use a different prior range for the base factor calculations. So ideally, you would use exactly the same, but it's not necessary. I use the most conservative choice of priors for the base factor calculation. And it looks exactly the same as the previous one. It's just you fill in an array for BF min and BF max. And then there are control system parameters. You really don't have to change any of those. There's only one fudge factor, and it doesn't fudge very much. And that's down here, this K alpha 1. And so basically, if you're dealing with a 1 or 2 planet, that should be somewhere about 0.91. And then if you're dealing with an 8-planet model, that should be somewhere up about 0.96. So it's not a very big range. But it's an attempt to do a little bit more optimal functioning of the control system. And really, you shouldn't have to touch that. The starting sigmas, there's nothing really to be done here because the program automatically starts off with proposal sigmas that are 15% of your prior range. So whatever you put in your prior range, it will start from that. You don't have to do anything there. Another option, though, is if you've already run many times this program before with this data, you can, as an option, you can put in the previous set of proposal sigmas that you found from the previous run. But normally that's not what happens. Then the gene boundaries. So here's where you specify your genes. So I'll say a few words about that. And first of all, some of you may be under the misapprehension that I am doing the genetic algorithm post-burn-in within the MCMC. That is not what's happening. So I'm using the genetic crossover operations only in the burn-in phase. it's happening within the control system. So I'm taking iterations in the burn-in phase from the MCMC chains, and I'm taking the best current solution that's coming out, and I'm basically going to breed that solution with the current best solution that has been found up to now. And so you can imagine just taking your list of parameters and making, making a gene out of the list of parameters, and you have the current. This is the parameter set coming out that's current best from all of the different chains, and you can then breed that with the gene, which is the current best parameter set up to date. So you can take a random cut here and basically swap this portion with this. And so you put this with this and this with this, and see if that is a better solution. Now, this doesn't work very well if you have multiple planets. It turns out that if you have multiple planets, it's much better to basically think of the set of 5 parameters associated with each planet as a separate gene, and to use the boundaries between those genes as places to cut and to match. And so you can cut out a gene from this one and swap it with the corresponding gene in the other one. And so this, and then do the calculation of the likelihood, the posterior, to see whether or not you've bred an improvement. And so that's, here we just specify what goes into each gene. And as far as, well, how useful is this? I probably, it's probably about time that I reviewed this, but when I did set this up, what I found was that the genetic algorithm would lead to improved peak values in the posterior, 30 times more likely, more often, than the regular MCMC plus parallel tempering. So it definitely speeds up finding the global peak, or interesting peaks. But once we've done the burn-in, it's no longer used. Well, it is used. It keeps going on, but it doesn't get, the MCMC doesn't know about it. It's all happening in the control system. But if it does succeed in finding and breeding a new solution that is much better than what's currently being found in the MCMC, it will restart the chain again. So it'll expand the burn-in period and put that new solution in there to be explored as if it came up from below from the tempering operation. And we then basically start gathering data after that. So there are certainly occasions where I've been going along and I thought, oh gosh, I'm in equilibrium. I'm in equilibrium. Whoops, it jumps. And this has happened 100,000 iterations into the cycle. So it definitely does. And effectively then I'm starting from there onwards, and that's now the new data. And I consider all the rest before that as burn-in. Okay, so it's very simple to do that. And I thought I'd automated that. It's funny. Okay. Well. So then here's where we calculate the likelihood. And also there's some normalization factors for the priors that are used in the likelihood. And so this is set up so that you shouldn't have to change this. It automatically does it for you, provided you don't, for example, you'd only need to change this if you, for example, added a slope as another parameter. then you need to put in the prior for the slope. But it's all set up so that it knows how you specified how many planets there are already, so it automatically will evaluate these constants. And it's set up for a 1 over frequency prior here or a 1 over square root frequency. I find that it's useful to use both. Try one run at 1 over mu and then another run at 1 over the square root of mu, just to make sure that there isn't some peak that you've missed that's relevant. Likewise, when you go into the likelihood calculation, well, here's where we pulled together the prior and the likelihood. Here's where the eccentricity prior is specified. This is itself all automated as well. It's automated provided you use the format that I suggest in putting in the parameter information. So anything like a planet should go at the beginning, because that's a repetitive parameter cycle. And then things that are not part of that repetition, like the drift velocity and S or slope, they go at the end. And so then this thing automatically extracts the cycles, the repeats of the parameters, and then does sets up the calculation to convert the measurement times to angles. And this is this differential equation, of course, is the thing that takes up most of the time. And here we are constructing the model, and here's the log prior with the eccentricity term, and then there's these other k max dependent terms as well. There's not much to be said about this, but here, here's the error vector, and I'm going to calculate the quadratic sum of the error vector and the S parameter, that extra noise parameter. And that's what's going on here. So here's the data minus the model divided by that error vector. And when I do the dot product, then I've got the square of that. And here I've got these normalizing factors, log fact, and the log of this error term. And then it puts out a result here, AVS, which is the list of parameters. And then it also tells you, this section here tells you the ordering. Remember I said that these planets will jump around, the periods will jump around. So what was the lowest period becomes a high period at some point. So you can find out, and you need to know for the relabeling, you need to know the ordering of the periods. So which came first, which is second. So this is, that ordering is extracted here and added onto the parameter vector. There's another likelihood term down here, which is used, it's almost identical, except it does everything in frequency. Up here, it's assuming that the parameter comes in as the frequency parameter comes in as a period, and has to you take 1 over that. Okay. I've hit the magic hour, have I? Yeah. So those are the inputs. You don't really need to change anything to the proposal distribution. There's a module here that decides on accepting and what to do with. There's a whole bunch of stuff goes on in this module. I call it generally the acceptance module. And here's another part of the control system that adjusts proposal signals, sigmas in the second stage. And then here's the kernel down here. This is the kernel. You don't want to change that. You'll almost certainly make a mistake. It's not anywhere near documented well enough to play around in this area. And it goes on for a long way. I think probably I was asked to stop at 12:30, so I think I better not eat into the poster presentation time, and I can, if there's interest, I can continue with this on Monday. Okay.